presentation will be by Professor V. Raghavan. Professor Raghavan is an assistant professor in IIT Madras. His research interests are droplet vaporization and combustion, laminar flame and its stability, heterogeneous combustion and its modeling. I now request Professor Raghavan to deliver his presentation.
I thank Professor Mahesh and Professor Sujit for arranging this talk for me in Indo-US forum. So today we'll talk about research on evaporation and combustion of isolated spray droplets. So liquid fuels are injected, so we have been seeing that through various atomizers, etc. And spray of droplets is formed and they reach the combustion chamber. So the reaction zones are formed either in the region surrounding these droplets, the diffusion mode, or where the fuel-air ratios are in within the flammability stoichiometric limits, they can form the premixed flame. So two types of combustions are seen in a spray environment. For studying the spray combustion, it is not easy to just go and study the entire spray combustion because of a lot of complexities involved. For example, the complete knowledge of vaporization and combustion of individual droplets are needed. For example, what is the rate at which a droplet is going to vaporize or burn? So that should be first studied. Then the interaction between the droplets. Basically, the interaction effects in atomization is one way. In the burning scenario, it is other way. So that should be taken into account. Then the statistical description is needed again. So direct study of spray combustion is very difficult. So we need to first understand some basics. So this is like a characterization study, basically. So spray combustion systems are classified into many, just listed here. So pre-vaporizing systems, then liquid fuel rocket engine, basically. So these are somewhat simple, and one-dimensional models also can do. But anyway, the realistic results need more analysis on this. Then if you take a gas turbine combustion, it's a multi-zone process which takes place in this. Again, the atomization, etc. So there we can see the various zones. And the diesel engines are very complex. The highly complex is the diesel engine spray to just simulate the entire spray or understand what is exactly happening there. So the process itself can be like this. For example, the vaporization, directly after atomization, vaporization can occur and gaseous reaction can take place. Or the atomization can lead to droplet collisions, and again bigger droplets can escape through, and droplet burning mode can also be there. So the premixed gaseous flames as well as heterogeneous flames can also be present. So we really need to concentrate on this. So in this talk I will be concentrating on the droplet evaporation and burning things. So as per the Chu et al. Paper, he has actually classified the spray combustion modes into these things. See, for example, if you take, this is the major burning area. So if you see the spray is coming from this, and you can see all the spray droplets evaporate before reaching the flame zone. So that means that only the vapors, the fuel vapors are supplied into the combustion zone here, or the flame zone, basically. If you come here, here there will be non-vaporization droplets also based on the density of the spray. So here, if the spray is actually not very dense, you can see that all the droplets will be vaporizing and the vapors are supplied to the combustion zone, basically. So, but if you have a bigger droplets, etc., you can see that individual droplets can cross the flame zone and burn with individual flames. So this is what which is called as heterogeneous combustion. And when the droplet sizes are very high, everything will be heterogeneous in nature. There will be no premixed type of flame zone, etc. So we will be able to talk, like we will concentrate on these particular areas where we have a droplet combustion and evaporation, which are very important in the system. So as I told earlier, the droplet combustion studies first arise due to the complexity in the spray. Second, it is due to the droplet interaction with the gas phase. So the heterogeneous type of interactions are to be taken into account. Then the burning characteristics of individual droplets should be under. For example, if you have a Lagrangian or model for particle tracking, if it is actually vaporizing, we need to know at what rate it vaporizes before it fully consumes the liquid inside this. So these things are to be studied. So for that, basic combustion studies are required. So starting from the classical study, see this is actually given by Spalding, the d square law, where the droplet, if you track the surface of the droplet, surface area of the droplet, with time it regresses with a constant slope k, which we call either a evaporation constant or a burning constant. So this is actually possible due to the density difference between the liquid phase and the gas phase. So to simulate such a steady droplet evaporation or combustion, basically, we have actually, Spalding has actually set up what is called a porous sphere experiment. So in which what we try to do is, through an infusion pump and a syringe, we try to inject the liquid fuel at the exact rate which is actually at which it is burning. And this is this porous sphere. This is a porous sphere which is made of inert material, and the liquid which is supplied into it will be burning on its surface. And with a wind tunnel, we can subject that particular sphere to various relative velocities. So we can see that at a lower relative velocity, see how we control the mass burning rate is as follows. So if you supply the sphere with a particular amount of fuel flow rate, then there are two conditions possible. If the evaporation rate is higher than the supply rate, then this entire surface will not burn properly. So if you overfeed the fuel into the porous sphere, then what will happen is the excess fuel will just drip out. So there is a maximum fuel flow rate which can be supplied for a given sphere diameter and the velocity, air velocity. So under such conditions, you can have an envelope flame in which the flame completely catches up this. So it's a steady burning. You know that now the fuel is fed at the exact rate at which it is burning for the particular condition. So for a given sphere diameter and this is not going to simulate the exact droplet, but it is going to characterize the fuel and let us know what is the rate at which it is going to burn. So when you increase the velocity, so one more advantage of this setup is when you increase the velocity of this air which is coming from the bottom, the flame which is actually enveloping the droplet will transit to what is called a wake flame. So now you can see the flames which are burning in the wake region of the sphere. Okay, so now for every condition we can have a particular burning rate. So what are the quantities which we can get from this is the mass burning rate. So for a given diameter and relative velocity, I will get what is the rate at which the fuel is burning. So I get the mass burning rate. So I can correlate the mass burning rate with some Reynolds number or some non-dimensional parameters. Here we have used what is called effective Reynolds number, which is nothing but which takes care of both forced convection as well as the natural convection due to gravity. So such type of correlations. So this is actually, there are two correlations which is given here. This correlation is for the envelope flames, and this is for the wake flames, like when the flame has transited over the droplets. So both the flames are actually important, and this study of envelope and wake flames can also give us a single step or overall chemical kinetics for a particular fuel. For example, if you take this study and you note down the Reynolds number at which the envelope flame shifts to wake flame. So under that condition, we can correlate what is called damp color number versus Reynolds number. So above this, when the damp color is high enough, then we will get what is called envelope flame, and when the damp color number shifts below a particular value, you get what is called a wake flame. So using this type of correlation of Reynolds number, we can generate the single step kinetics parameter, which we have done for ethanol air, and we have proposed something which is actually useful in some engine studies or any combustion systems where you use ethanol or any type of fuel can be used. So this type of characterization studies, either you get the burning rates or the kinetics parameters are done using this porous sphere setup basically. And also one more advantage of this porous sphere setup is not only the single, like for example, it's ethanol gasoline blends. So unlike that, you know that these two fuels are going to preferentially vaporize. So one is going to vaporize faster than the other and something like that. So now what happens in this porous sphere setup, we are supplying this same constant like a blend composition continuously. So for example, if I fix 30% of volume of gasoline in the ethanol gasoline blend, then I ensure that this composition is fed continuously, at the exact rate at which it is burning basically. So, for a given composition, for a given sphere diameter and the air velocity, I can get the mass burning rate. So, but in a transient experiments, we will not be able to do that basically. So, for example, if you have a liquid droplet which is first initially having a composition of say 30% gasoline and ethanol rest, then what will happen is preferentially ethanol will vaporize. So, after a time instant, we will see that the composition would have changed. But in this steady apparatus like the porous sphere apparatus, we will be assured that the composition will not change because we are feeding the fuel blend at the rate at which it is burning. So, that is one of the advantages. So, we this gasoline and like whatever be the blends, you can use it basically. Then coming to the numerical simulations, there are two types of, so now this is what we have seen just now as the steady state burning of burning analysis. Now, if you have a transient studies, actually I am going to talk about some numerical studies. There are two types of studies possible. One is the suspended droplet. So, again to see how the droplet burns, what is the droplet lifetime and etc. Another one is the moving droplet. So, in the suspended droplet, only the diameter is going to decrease with time and the velocity, relative velocity will be kept same. But in the moving droplet, due to drag, the velocity also is going to decrease. So, for example, if you see the simulations here, this is the simulation for suspended methanol droplet basically. So, what happens is initially in the relative velocity, see the air is blowing from this direction. So, initially due to higher relative velocity or Reynolds number for example, you can see that the ignition occurs here and you can have a wake flame and slowly when the droplet diameter reduces, the Reynolds number reduces and the flame is trying to catch up the droplet. So, droplet is not moving, but the diameter is slightly decreased. So, since it is a low velocity, before the droplet has reduced to a very low diameter, the flame has enveloped the entire sphere. So, this is what actually we will see. When a droplet moves into a hot chamber, it gets ignited and an envelope flame is formed. So, this type of simulations are possible with a two-phase model. Similarly, if you do a moving droplet simulation, you can see that the droplet moves from say right to left. You can see first when the droplet is moving like this, the ignition is occurring here. So, the evaporated vapors come to the wake region of the droplet and ignition occurs here and the flame comes and catches the droplet and you get the envelope flame at some time instant of the moving droplet. So, now here you can see that the droplet diameter also should reduce and the velocity also is going to reduce due to drag. So, this means that the moving and stagnation like stagnant droplets, suspended droplets are not going to give us same results for every Reynolds number range. So, for example, if you take a very low Reynolds number, for example, say 6, initial Reynolds number 6 based on the droplet diameter and the relative velocity, you can see that the suspended droplet is slightly higher, the K value, the burning constant what we call, K value for suspended droplet is slightly higher than that of the moving droplet. You can see that slope also is, initially there is some transient due to ignition, after that the slope is actually almost constant. Then if you take higher, for example, this is the Reynolds number 8 and this is the Reynolds number 50, very high Reynolds number. You can see that, you can see that for Reynolds number 8, the moving droplet is giving a higher burning rate constant than the suspended droplet. This is because of the fact that for the moving droplet, there is an envelope flame formation at some time instant. But for suspended droplet, envelope flame is not formed at all because the relative velocity is very high, the envelope flame is not formed at all. If you take the Reynolds number of 50, for both the droplets till about say 0.2 seconds, the flame is only wake flame. So, the entire droplet is not engulfed by the flame. But at the end of the lifetime, you can see the sudden increase in the burning rate constant for the moving droplet, which is actually due to the increase in the envelope flame being formed at that time instant for this. So, for moving droplet, it is seen that at some instant of its lifetime, an envelope flame is formed somehow. So, that this means that for all the range of Reynolds number, I cannot have a, see if there is a envelope flame formation at the beginning of the lifetime itself, then the moving droplet and suspended droplet will give same type of results, but not otherwise. When there is a lag in the formation of the envelope flame, you can see that there is a drastic change in the results. So, appropriately we have to choose models and see the lifetimes, etc. Similarly, this is about N-heptane model. What I have shown earlier was for N-heptane. So we can also do for alcohol droplets, but alcohol droplets has a lot of complexities. For example, if you see here methanol, produces a lot of water due to the 2 moles of water per mole of methanol, and the water condenses on the surface of the liquid droplet. And what happens due to this, due to high polarity between the methanol and water molecule, the water is actually taken inside the methanol droplet. For example, when the droplet starts burning, products are formed and the water vapor is going to settle on the droplet surface. After some instant, we will find that the liquid droplet will be composed of more amount of water than methanol itself, because methanol preferentially evaporates faster. So due to this, see actually this normally due to convection there will be a liquid phase motion, and liquid phase motion can also come due to this. See, a flame standoff here is less, and here it is more. So that will be a temperature gradient along the droplet surface. So due to this, thermal Marangoni effects can come into play, and this also can trigger some internal circulation. And one more thing, due to water formation here, along the surface the water will not be same, uniform. Okay, so because the water formed can be higher here and very low here. So due to the concentration of the water along the surface, solitary Marangoni effects can also come into play. So due to this complex behavior, we can see the circulation patterns. Actually, this is actually simulated by a two-phase model. You can see the complex circulatory patterns are seen in the droplets till the end of its lifetime. See, for example, the droplet diameter is decreasing with time. Until the end of the lifetime, we will see that a lot of complex structures in the liquid phase is formed due to the thermal Marangoni and solitary Marangoni effects. And also, there are several causes that the flame around the droplet can extinguish. For example, due to convection, it can extinguish. If we see that the wake flame is there, due to high convective flow, when the droplet diameter reduces or the droplet velocity decreases, you can see that the wake flame transits to envelope flame. So convective extinction is possible. But in alcohol droplets, more than that, the water content is what? So water mass in droplet actually steadily increases, and at a particular at the time of extinction, you can see that about 75 to 80% of the droplet will be composed of water only. So alcohol droplets has this problem actually. So we need, when you model the characteristics of an alcohol droplet, we need to take into account of surface tension effects in the interface. So in the interface coupling conditions, you need to take surface tension effects. So that is what is given here. And similarly, even for alcohol droplets, the thermal radiation by the absorbing species is very important. So for example, if you have a droplet diameter more than 1 mm, okay, so then we need to actually have the surface tension effect as well as the radiation effect to predict the extinction diameter for the particular case. Then when you come to the high pressure droplet vaporization, there are other complexities. For example, the non-ideal behavior in the gas phase is there for the very high pressure. See, if a particular fuel droplet is vaporizing in its own vapor, then the critical conditions are defined properly. For example, for kerosene, it is 18 bar pressure at which it is critical pressure for the kerosene. Similarly, at some temperature. But when you have a binary fuel, for example, kerosene vaporizing in a nitrogen environment or something like that, then you have a critical mixing state which can go well above the temperature. For example, the ambient temperature may be supercritical, but the droplet surface will not attain that supercritical temperature faster. So the critical condition for the binary mixture will be very late actually. So we try to do the kerosene, actually we did only its surrogate, we did endo-decane. If you see that when we kept the pressure, this is actually for several pressures. See, for example, PR is reduced pressure from 0.5 to about 6 we have simulated, and the ambient temperature was kept as 2 times the critical temperature of the kerosene, like the endo-decane. So you can see that there is no d square law followed for high pressures. When you go for low pressures, after some time period, at least the regression follows a constant slope, but not for higher pressures. Similarly, if you take the central, the temperature of the droplet center and the surface, they don't reach equilibrium. For example, in a low pressure situation, you can see that the temperature of the droplet surface will be higher than that, but soon that center temperature will catch up that. So there will be the local equilibrium, but in this case it is not there at all. Similarly, if you see for a particular condition, when the reduced pressure is 6, that is the ambient pressure is 6 times the critical pressure of the liquid fuel, you can see there is a critical state which is attained. So after that there is no difference between, there is no interface, the interface vanishes, and liquid and vapor will be just, we call it fluid. So this is actually high pressure stagnant droplet vaporization. The droplet is there, and there is a relative velocity on this. But actually the Reynolds number is very low for this case. And if you have a moving droplet, we tried, we were simulating only spherical droplets. So we were sure that the Weber number should not be more than 1 or something. So we choose a velocity of the initial velocity of the droplet as 1.5 meter per second, and the droplet's diameter was about 100 microns. So if you see that again, when the velocity is actually increasing, the droplet lifetime decreases, and it is completely transient. So there is no equilibrium evaporation occurring at all for these conditions. Like if you take a pressure of about 4 times the critical pressure and ambient temperature of about 2 times the critical temperature of the endodecane, we don't get any equilibrium evaporation at all. Everything is transient throughout. Then the fuel blends are nowadays used in any system, like in engines. For example, biodiesel and diesels are used. So again, we can do the burning rates of that in a steady apparatus, what we have seen, like in a porous sphere apparatus, we can see the steady burning of these blends. But when these experiments are carried out for several composition and diameters, etc., we will be able to do the like a transient analysis also. So such an analysis is done here. For example, if you see, we have taken two, like the case of diesel and Jetrafa biodiesel. So Jetrafa is a non-edible oil which is got, and when you esterify it, you will get the Jetrafa biodiesel. So in various blends, we will get this. Similarly, Karanja is another non-edible oil, using which we got another biodiesel. So we tried to do the analysis for this. You can see that the diesel is here, which is having a highest burning rate, and Jetrafa is having lower burning rate, and these are all straight. See, this means that the diesel or Jetrafa burn as a single component droplet basically, but the blends exhibit a multiple component behavior here. So there is a change in slope. You can see there is a change in slope in this based on the amount of diesel or Karanja which is present. So when you investigate the mass burning rate, temporal variation of mass burning rate, you see there will be 3 zones basically. In the first zone, for example, this is diesel, this is the diesel curve, and the Jetrafa 20% and diesel 80% will actually have a first mode of operation where only diesel will burn. Then after that there is a combined burning mode in which there will be some change, like all the three curves are visible here. So this means that this blend is having different burning rate than that. And finally, if you see this third Jetrafa's curve, so this means that there are 3 distinct mode based on the amount of biodiesel you inject in the fuel. So these things can be done by the as a part of characterization studies basically. And finally, I am going to just talk about again the same porous sphere experiment can be used to see what is the interaction between the droplets. For example, when the 2 spheres are burning one over the other at several distance. See, for example, you can see the larger sphere is burning here and the smaller sphere is burning over it at a particular distance. Okay, so when the distance is not much large, then we can see that the flame from the first droplet is going to interact with the second one, and even the velocity is very high here. So the first droplet in the bottom has a wake flame, but the top droplet has a envelope flame. And when the separation distance is increased, two individual flames are got. They don't interact at all. So, and also you can see that when the larger droplet is burning over a smaller droplet, the oxygen starvation is one of the important thing which is observed. This droplet has a wake flame, and here you can see that the vapors are going and there is a flame zone beneath the top droplet. And one more, at a particular separation distance, we see that this droplet extinguishes whatever be the number of times you ignite it, because all the oxygen is taken by the top droplet and the bottom droplet doesn't burn at all. So these are some basic interference effects which we can verify. And similarly, if you see the mass burning rate is affected thoroughly when you have a droplet which is burning on the bottom.
Thank you, Professor Raghavan. We have time for two questions, perhaps. Two quick questions.
I have one question that when you are looking at increase in your experiments, when you are increasing the airflow rate at a very low airflow rate, when you are having the envelope flame, it looks blue, but as your airflow rate is increasing and you have a wake flame, it's becoming more yellowish. I mean, why is it? I mean, I would expect that when you are having a wake flow, it's more premixed. So.
But the fuel is not actually finding all the things. See, the fuel itself is carried away from and it is burning in the wake flame. So not much air is going to enter in the wake region alone. So that is the problem when in wake flame cases. If you increase the velocity more, after a particular, see, once it transits, it has like a orange color. So once you increase the velocity further, before it's going to extinguish, we will see that it will be a pure phoenix flame. Because now what happens is there is a sudden drop in the mass burning rate, then the mass burning rate starts to rise basically. So at one particular condition only you will be able to see whether the premixing, the oxygen diffusion into the wake zone is not possible because fuel rich zone is there. Okay. So that is giving the orange color. So once you increase the air rate further, you will get the premixed type of flame.
And one more question.
Yeah.
If you are, when you are studying the blended fuels with the porous sphere thing, I mean, this combustion of blended fuel, it's typically a transient phenomenon. Okay, so I mean, because it is always the burning rate is changing, fuel composition is changing, so how can
the fuel composition will not change. That is the infusion pump is a displacement type device. So you have a constant blend there and you just push it at a particular rate, it burns. Normally we will try to overfeed that and try to reduce the fuel speed rate, so that see, this is like this, the feed rate increases and reaches a maximum. So we will always try to get the maximum burning rate for every condition. So in that case, we will get for a single composition you can study. In a suspended, like in a liquid droplet studies, it's not possible. In porous phase study alone, it's possible to change the composition also and study.
Actually, in one of your plot I saw, particularly I think numerical prediction, d by d naught square versus the time non-dimensional, there is a little increase in the diameter. Yeah. Like could we, comment
the
on
droplet? Actually, what happens is if you have a multiple droplet first expands. The volumetric expansion of the droplet takes place. Basically, in any oil or alcohol droplets, you can see that first the volumetric expansion will take place. Then only the droplet will, so the initial heating will increase the diameter first. Due to the volumetric diameter, the d by d naught will increase more than 1. Then it starts vaporize. So those period, the increased period is the important.
But you will be taking the droplet diameter, not the gaseous envelope.
No, droplet diameter only I am saying. It's a droplet diameter, yes.
The d naught is the initial diameter. That's what I get.
D naught is initial diameter. After a time instant,
that in principle should not go beyond 1, but no. It has gone in some initial phase.
In a liquid droplet scenario, it will go.
It
is called volumetric expansion.
That's what he's referring to. That's a droplet inflation. It normally happens. Is this the Wittig's paper that you took from the results?
No, it's my own work.
Okay. I guess we can continue the presentation during the coffee break. So let's thank Professor Raghavan for this presentation.